2.4 is looking at the average rate of change of a function. So we start out with just a generic graph of a function here, say f of x. And the question is, well, I'd like to know the slope of this function, but the thing is that if you look at the graph here, you can see that the slope changes depending on where I am on the graph, because this is actually not a linear function, it's not a line. In other words, it doesn't have a constant slope across the whole domain. However, well, I bet I could approximate the slope of the function. So say I pick two x values. We'll call that one x equals a, and that one say x equals b. And what if I connect the two relevant points on the graph here with a line? So what would that line look like? Something like that. The name of that line, by the way, is the secant line. Okay, so what I could do is I could find the slope of that line. Okay, now that wouldn't be exactly the slope of the function, but depending on how close that line is to the function in that region, I could get a pretty accurate estimation of the slope of the function by finding the slope of the secant line. Okay, so in order to find the slope of that secant line, I have to remember the formula for finding the slope of a line given 2 points on the line. Okay. And so what I'm going to do is I need to look at the relevant points, and I'll need to fill in the coordinate pair. So I'd have A. To get the y value, I'd have to plug a in the function, so f of a. And then I'd have b and whatever f of b is. Okay, so now I'm thinking, okay, this is, we'll call this one y2, this one y1, say. Okay, so when I fill in over here, I have f of b minus f of a. And then here's x2, here's x1. Okay, so this formula, move this down, try this again. Move this down here so there's a little bit more room. This is actually the formula for finding the average rate of change of the function f of x from x equals a to x equals b. Okay, but I mean, all this formula is it's really just a fancy way of writing the slope formula. It's just y2 minus y1 over x2 minus x1. And then let me change one thing here. When I plugged my x's in, I meant to use my x's from my coordinate pairs. Should be b minus a. Okay, but anyways, the same thing, right? Different notation. So what I have in the numerator, this is y2, this is y1, this is x2, this is x1. So what does this give me? This gives me the average rate of change of the function, which is the slope of the secant line, which is an approximation of the slope of the function itself. So let's look at a couple of examples. So here I have example number 1. Find the average rate of change of the function f of x is x squared plus 2 from x equals negative 2 to x equals 1. So all I'm doing is I'm setting up the slope formula. So look, here's a, here's b. So what I would do first is I would actually go ahead and calculate the y values Okay, so I can fill in these coordinate pairs. So let me see. So what is f of -2? It's -2 squared plus 2 is 4 plus 2 is 6. And then this one, this is f of 1, so 3. Okay, and then look, here's my setup for my average rate of change. So it's y2 minus y1 in the numerator, and then x2 minus x1 in the denominator. And then I just simplify this. Okay, so this is the average rate of change of f of x on the interval -2 to 1, or from x equals -2 to x equals 1. So I'm kind of just curious about, well, what's actually going on graphically here? So we could look at that for a second. So if you think about the graph of this function, I'm just going to do a rough sketch. So this is a parabola shifted up 2. Okay, so I have 0, 2. If I plug 1 in there, I have 3. If I plug 2 in there, I have 6. Okay, and then this is symmetric over the y-axis. It's an even function. So I can fill in those mirror points. So there's my rough sketch of f of x. So I'm just kind of interested in, well, what did this calculation in part 1 really give me here? So we said from x is -2. So here's that point. So that point we found was -2, 6. And then 2x equals 1. That point we found was 1, 3. We found the slope of this secant line. Very good job drawing that. Okay. But what we determined was the slope of that secant line was -1. So does that look accurate? Down 1, right 1, down 1, right 1. Indeed it does. Okay. So we found that the average rate of change, or the average slope of that function in between -2 and 1 is -1. Now, I mean, those points are pretty far apart, so I would say that doesn't really give me a very accurate estimation of the slope of the function itself on that interval. But it does give me an estimate, an approximation, or an average. So let me try another one. So again, these are really easy. These are just slope problems. Okay, so the average rate of change is just the slope of the secant line. So we have y2 or x2 minus x1 filled in. It's just looking at these. Then I need to get the matching y's, right? Because I have to fill in the coordinate pairs. Okay, so what is f of -5? That'd be 3 over -5. -3/5. F of 2 would be 3 over 2. So let me fill those in. 3 over 2 minus -3/5. Let me make sure. Look, so here's y2 minus y1, and then x2 minus x1. Okay, so then 3/2 plus 3/5. 2 plus 5 is 7. So from here I have a couple options. So I need an LCD, so I could multiply each of these fractions individually, like 5 over 5, 2 over 2, combine all this, then I'd have to take the first fraction, I'd have to flip the bottom fraction, multiply. Okay, I can do that. If I do everything right, I'll get the correct answer. But what I'll do instead is I'll use this method. It's going to save me a lot of work. So I'm still going to find the LCD. So the LCD of 2 and 5 is 10. But what I'm going to do is I'm just going to multiply the whole numerator and denominator by that value 10. Because look at what happens there. This is actually going to work out pretty nicely. Okay, so I distribute the 10. Okay, so 10 divided by 2 leaves 5. So what do I have from that first fraction? I have 5 times 3. Okay, what about the second fraction? 10 divided by 5 leaves 2. So I have 2 times 3. The bottom, it's just multiply straight across. 7 times 10. 15 plus 6 over 7 times 10. Now I'll leave the denominator factored because what you'll notice is that with a lot of these, you're going to actually get a cancellation. So you don't actually have to compute the big number because look, 21 divided by 7 is 3. So aren't I left with 3 over 10? Okay, so what is this thing? Well, this thing has a few names, a few interpretations. This is the average rate of change of the function on the interval -5 to 2. This is the slope of the secant line on that interval. So it's an estimation, or it's an average of what the slope of the function actually is on that interval. Okay, so let's do one with the same function here. But this time, instead of looking at numeric endpoints, okay, like instead of looking at from numbers A to B, what we're going to look at is we're going to use some variables for endpoints. So we're going to say, well, I'm going to set this up the same way. So what if I start with A and end with A plus H? So why would I want to do this? Well, actually, this calculation where I'm using the A and the A plus H, this is actually an important calculation for calculus. So at the end of this class, we're going to talk about the difference quotient and the definition of the derivative. And you're going to see this calculation again, where we're looking between A and A plus H. Okay, so for now, we'll just do the algebra. But you will see this again, and we'll look at the interpretation later on. Okay, so there are my 2 points. Then I set up my slope, same as the last one. Okay, let me go ahead and cancel in the denominator. Okay. So now I'm going to use that same trick. So what I'm going to do, I'm going to actually move this down so I have a little bit more room here. And what I'm going to do is I'm going to multiply by the LCD. Okay, so in this case, I need a factor of A and a factor of A plus H. Okay, one from each of those denominators. So I use that same trick. So I distribute. So here the A plus H cancels. So what I'm left with is the 3 and the A. Okay, so that's 3A. Then when I distribute to the second fraction, let me see, let me use a different color. So I take this and I distribute to the second fraction. Color's not very, right, let's try that one. Okay, so I distribute to the second fraction. Here the a cancels, so I'm left with the 3 and the a plus h. So I have 3a plus h. The denominator I just multiply straight across. So actually, you see there, I actually made this problem pretty simple. Now I distribute that 3 and combine the like terms. So that's a pretty handy trick. Okay, then these cancel. So it's -3 over a plus h. So there's my simplified average rate of change of f of x on that interval a plus h. Okay? And so you notice there that I have variables in the answer, but that makes sense because you see how I plugged variables in for the endpoints. It would make sense that my answer there would have variables in it. Okay, let's see what else there is. Here's a little word problem. Okay, so here we have an object travels a distance, d of t is square root of t feet in t seconds. Find the average speed from t equals 1 to t equals 4 seconds. So in other words, we're finding the average rate of change of this distance function between 1 and 4. So same thing we've been doing. So let's see. The average speed, it's going to be my average rate of change. And I have to find these values. So f of 1, square root of 1 is 1. So I'd have the point 1, 1. F of 4, square root of 4 is 2. 4, 2. Okay, so I already set up my denominator. 4 minus 1. My numerator is going to be 2 minus 1. So 1/3. Okay, so then anytime I'm doing a word problem, I have to do some sort of interpretation. I have to put some units, and I have to kind of write out a statement. What does this mean? Okay, so what are the units? So this is a rate. This is a speed. Okay, so then look back at the units in the problem. Feet and seconds. So this would be feet per second. Okay, so what would I say? The average speed of the object between, 1 second and 4 seconds is 1/3, or I guess I could say 0.33 feet per second. Okay, so here's another part. It's the same thing. That's part of my answer then. Find the average speed from 4 to 9 seconds. Okay. So f of 4 we already found, didn't we? So let me write that point. That was 4, 2. Okay, if I plug 9 in that function, square root of 9 is 3. So this is very easy. So it's y2 minus y1 over x2 minus x1. So what is this one? 1/5? Okay, so what has happened to this object? I guess it's slowing down, isn't it? Because from 1 to 4 seconds, its speed is 1/3 feet per second. But from 4 to 9 seconds, its speed is 1/5 feet per second. So there's that. So then let me write. So let me just, don't know, should I copy this? I have to rewrite that. Try this again. Copy. Put that there. Same thing, but then let me change these. Okay, so then what is this one going to say? The average speed of the object between 4 seconds and 9 seconds is 1/5, so 0.2 feet per second. Okay, so there's that, and then there's that. Find the average speed from 4 to 4 plus h seconds. So this is another one of those parts where we're going to have variables in the answer. Okay, but other than that, we already found 4/2. If I plug 4 plus h in the function, that's square root of 4 plus h, right? Yeah, okay. Okay, so then I'll expect my answer to have variables in it. Root 4 plus h minus 4 over, oops, make a mistake there, I did. Let's double check. So I should be y2 minus y1. That should be a 2. And then x2 minus x1. And then I have to figure out how to simplify this. Okay, but I have an idea for that. Excuse me. So I'm going to use a trick that we're going to use several times actually throughout the semester, and I'm going to multiply by, this is called the conjugate. Okay, so I'm looking at that radical expression, and what I'm going to do is I'm going to take that expression, and all I'm going to do is change the middle sign. So instead of minus, it's going to be plus. I put the opposite sign. Okay, now I have the same expression top and bottom because I'm really just multiplying by 1. So again, that thing's called the conjugate. Okay, so now the denominator, just multiply straight across. The numerator, I'm going to do a FOIL. So look, I'm going to multiply this root by itself. So that means I'm squaring that root. So that would just leave me what's underneath the square root, okay? Then look, I have 2 roots of 4 plus h minus 2 roots of 4 plus h. Those middle terms cancel. So all that's left now is minus 4. So this is why this works out so nicely, because I get a bunch of cancellation. Okay, look, even then I can even cancel h with h. So my result then would be 1. Write that a little nicer. Root of 4 plus h plus 2. Okay, so this is the average speed from 4 to 4 plus h seconds. Okay, the average speed from 4 to 4 plus h seconds. So again, this would be in feet per second. But let's see what else we can do. So use your answer to 3 to check your answer to 2. Okay, so how would we do that? Let's see what we found in 2. In 2, we had to find the average speed from 4 to 9 seconds. In 3, we had to find the average speed from 4 to 4 plus h seconds. Okay, so in other words, what would h have to be? So if I want to get from 4 to 9, isn't 9 4 plus 5? So in other words, wouldn't I be plugging h equals 5 into this expression? Okay, so one more time, look. To get from 4 to 9, well, 4 plus 5 is 9, right? So h would have to be 5. Okay, so if I plug h equals 5 in that formula, what do I get? I get 1 over square root of 9 plus 2. 1 over 3 plus 2. Oh, look at that. I get that 1/5 feet per second again, which let's see if that's what we got. Yes, indeed. Okay, so I was able to check that answer. Okay, so I guess looks like there's one more part. Hold this up a little bit so we can. What does the average speed found in part 3 approach as h approaches 0? Okay, so here's the average speed found in part 3. Okay, so what happens to that as the h gets close to 0? Well, if that h goes to 0, wouldn't that just leave me with 1 over root 4 plus 2? 1/4? So the average speed approaches 1/4 or 0.25 feet per second as h approaches 0. Okay, let me see if I asked. Well, let's see if we can do an interpretation. So what does that mean? What does the average speed found in part 3 approaches h approaches 0? So what was this? This was the average speed from 4 to 4 plus h seconds. Okay, so if h goes to 0, then wouldn't that just leave me with t equals 4? So wouldn't I actually just be looking at the instantaneous speed at t equals 4 seconds? Okay, so what does this represent? This would be the instantaneous, not the average. This would actually be the instantaneous speed at t equals 4 seconds. So that's kind of cool.